So I'm Colin Walls, I'm from Mentor Graphics, but Mentor Graphics is primarily known for hardware, electronic hardware design tools, but I actually work for Mentor Embedded, which is the embedded systems division of Mentor Graphics. And my interest is embedded software specifically. And that's what I'm going to spend a bit of time talking about this morning. It's at a reasonably high level. I would invite you to wave at me if you have a question, even though this is billed as a keynote presentation. I see no reason why this shouldn't be somewhat interactive. Keynote speakers often think that they have a big hill that they're standing on above their audience, and I prefer to communicate with people rather than speak at them, if you see what I mean. So, embedded systems. We all know what embedded systems are. Wherever you look, there are embedded systems. I was just trying to calculate in my head before I started speaking how many embedded systems are in this room. I suspect it is in the dozens. It might be in the hundreds. I walk around with several on my person at any typical time, and I think everybody is used to that fact. And of course, the design of embedded systems is something which is like any other electronics, a design exercise, and of course IP is involved in that a lot of the time, but from my perspective the really important thing is the fact that software is involved. I'm particularly interested from a sort of non-professional perspective as well as everything else in consumer devices. Actually, you all are. You're all consumers of electronics. You all have consumer devices. This market is interesting because it's very characterized by certain things. There tend to be huge volumes, and the purchasing decisions are interesting compared with other kinds of electronics. The buying factors that affect the products are brand. Now, as a software engineer, what influence do I have on the brand of a particular product? You might say none at all, but actually, as a software engineer, I can completely destroy a brand. I may not be able to create one, but I can destroy one. Because if the software behaves badly in a particular product, then that will damage that brand. I can give you a quick example. I'm not going to name the company, but many years ago I had a mobile phone, and it was designed by somebody the software was designed by somebody who had heard about phones but never actually used one themselves, I concluded. Because the whole menuing system was totally counterintuitive. Everything you wanted to do, you had to consider where you wanted to be and come backwards to get there. I would never buy a phone from that company again. They probably make much better phones now, but they messed it up at that particular point. So the software destroyed the brand in my eyes. Obviously, everybody's interested in the specification of devices, and you're interested in the price, of course. I'm going to use, for the rest of this talk, a specific example. I'm going to talk about digital camera. Now, I don't have any connection with the manufacturer of this camera. I don't have any inside knowledge of exactly how this camera works. I just enjoy using one, but I want to use it as a vehicle to consider where embedded software fits into modern systems. So, don't ask me any questions about the insides of Sony cameras. I'll happily tell you how good they are to use, but as I say, I have no business interest there. So, if we look at the digital camera, well, the first thing we can think about, and which is why they are so successful nowadays, is they require a lot of computing power. Something we could not have considered doing just a few years ago. To harness that computing power, you need an operating system of some kind. A real-time operating system is most likely in a camera, simply because it's a time-constrained application. It's quite possible that you have multiple cores in there. 2 or more is very likely in a digital camera. This presents some very interesting challenges for the software engineer. Debugging is one of them. Debugging is difficult when you only have 1 core. As soon as you have 2 cores, it's more than twice as difficult, and it carries on from there. It's also a challenge from the operating system point of view, because if you have multiple cores, you still need either an operating system or some operating systems. There are 2 different architectures we can consider here. There's what we call AMP and SMP. AMP is asymmetric multiprocessing, SMP is symmetric. Take a very brief look at what they're all about. Asymmetric multiprocessing is a very simple concept. You have multiple cores on in your device, or multiple chips possibly, but multiple processors anyway. And you run a separate operating system on each one. My example here, I have Linux on one, and I have a real-time operating system, Nucleus, on another. And I run the application code as appropriate on whichever operating system, and hence on whichever core. They communicate between one another, of course. So that's very simple, and that has the big benefit of enabling you to choose the right operating system for the right part of the application. So the real-time parts are here, and the non-real-time parts will be here. So, the only drawback of that is you have multiple cores here, and you cannot optimize the amount of power you were using, the amount of CPU processing power you were using, simply because the applications are fixed on which core they run. The alternative approach is to use SMP, symmetrical multiprocessing, and in this case, we simply have multiple cores, and we run one operating system on all of them. This means the operating system has control over where the code runs, on which core it's running, and therefore can optimize the use of the hardware. This is the way that laptop computers and so forth work, but it works just as well in a real-time context if you want to do that. So it really depends which architecture is right for your particular application. Once again, I have to say, inside that Sony camera, I have no idea what the architecture is. Sony won't tell me. But it will be one of these, for sure. One of the really big things that we think about on modern embedded systems and devices like this camera would be power management. What can we do about it from the software perspective? Now, many, if not most of you, are hardware designers. There's all kinds of things you can do to reduce power, and I'm sure you are very familiar with that. But where does software come into that as part of the exercise? Well, first of all, the choice of operating system. If we choose an operating system which is small, that means we need less memory means less power. If we choose one which is fast and efficient, we'll use less CPU cycles to get a job done. We might even be able to run with a lower clock speed, which will improve the power consumption. So there's lots of things we can do just by choosing the right operating system by selecting one off the shelf. The software can also be given control of the voltage and the frequency of the processor in order to optimize power consumption in that way. This is a dynamic voltage and frequency selection. That's a facility which is interesting to look at how it's used, because it's outside the normal space of expertise of software engineers to even think about this kind of thing. There are also low power modes. Most processors nowadays will have a selection of different modes. Typical low power modes are standby and hibernate. These don't have standardized names. I tend to use the names which are common in the desktop computer world. So standby is when everything is shut down, everything is powered down except for the memory which holds the code. So therefore, when you want to start up again, it will start up very quickly. Hibernate is when everything is shut down almost completely because the entire memory has been written somewhere safe, maybe to flash or somewhere like that. So it takes a little bit more time to start up. So all this software control of power consumption is the challenge which software engineers face in designing devices to have batteries that last more than 5 minutes. The approach that embedded software uses to this is to look at use cases. So you break down the application into different scenarios. So in the case of a camera, we may have use cases like this. So the camera may be off. We might think, well, off is off, but actually with the camera, off may mean different things. In the case of the camera I'm talking about, if I turn the camera on and I haven't used it for a long time, it takes a little bit longer to start up because it has to start up literally from cold. If I then switch it off and then 5 minutes later turn it on to make another picture, it will start up very quickly. And that's because it retains the bulk of the setup for a period of time. I'm not quite sure how long, but an hour or two from when you first turn it on. And then it goes into a completely cold sleeping state after that. That's very logical because it's better to turn the camera on and off as you need it. I'll come back to that in a moment. Other states will be right, switched on, ready to take a picture. It's sitting there waiting for you to press the button. You press the button to take a picture. That's another use case, another situation. You might be shooting a video as another possibility. You might be looking at pictures on the screen on the back. And you might be uploading images to your computer. Now, each of these use cases requires a different combination of hardware to be activated, a different profile in terms of the power consumption. So you require a lot more CPU power if you're shooting a video than you would be if you're just viewing the pictures. And you only need to turn on the USB hardware if you're uploading images. If you've got Wi-Fi and so forth, that's even more significant because the power consumption will be there. So each of these represents a profile of how the power consumption can be optimized by the software, remembering the software has these tools to play with. The last point I put down here is fast startup. Now, with any electronic device, there is a startup time. When you switch it on, the software has to get itself into the right state. I'm a very impatient person. I'm not very good at waiting for things. Now, this is kind of ironic. Let's move away from cameras for a second. At home, I have a TV, like everybody. I very rarely watch it. I don't know when people find time to watch TV. I don't really have much time for that. But I have a nice TV when I want to watch it. However, when I switch it on, it takes, I suppose, nearly a minute before I can actually watch anything. And that's because it's a state-of-the-art smart TV. It's got a boot and operating system and blah, blah, blah. It reminds me of my childhood when you turn the TV on and it used to warm up. Literally, all those vacuum tubes had to warm up. And in those days, there were probably 24 vacuum tubes. We now have 1 billion transistors, but we've gone round a complete circle and things take ages to start up. Now, okay, with the TV, it doesn't really matter. I'm just an impatient, difficult person. But with a camera, it does matter. And I will give you an example of how this matters. Many years ago, I used to do photography with my late wife. She was a very expert butterfly photographer. And we would go out looking for butterflies, and I would photograph anything else that was interesting to me. She would have 2 spare batteries for her camera in the pocket. I had no spare battery. We had different cameras. And why did she need so many batteries just to photograph butterflies? And the reason was that her camera had a rather slow startup time. It took several seconds to get itself ready to go. Now, when you're photographing butterflies, you're running around the field, you see one, and it's not going to hang around while your camera starts up. So she would leave her camera switched on most of the afternoon, and the lens would begin to, and it was eating power. Whereas my camera started up really quickly. So I would just switch it on, take a picture, switch it off. So my battery would last all afternoon. So this startup time can be absolutely critical. And I'm not going to say which brand of camera she had, but it wasn't a Sony, is anything I can say. But and that taught me some lessons about the practicalities of power management. Connectivity is obviously important. You're going to hear a talk in due course about IoT things. IoT is all about connectivity. In the case of a camera, we have 2 possibilities for connectivity, really, that come to mind. One is transferring of data, so the uploading of pictures, or even downloading of pictures if you want to, or the remote control of the camera from a computer. Typically, the interface will be USB. USB 3 is now commonly used, or 3.1 is the latest version. USB 3 is something I do a talk on occasionally. It takes an hour or so to cover an introduction to what USB 3 can do. But primarily, we get a much faster transfer time. And with modern cameras, we may often deal in raw images, which are quite large, or videos, which are very large. And therefore, the fast transfer time is important. And of course, the software has to manage all of this. Even though I'm a software engineer, I'm fascinated by the movement to what they call a Type-C connector, because there is a suggestion that in future, many electronic devices will have one connector on it, and that will be a single Type-C connector. In fact, the newest MacBook looks exactly like that, because that will provide power, will provide connectivity all in one connector. There's pros and cons of that, of course. Wireless is quite important. I don't actually use my camera wirelessly, although I could do so. Maybe I should. But it has Wi-Fi capability for transferring images, and Bluetooth is another option. So all of these require software support. Then the last area we look at is the user interface. It's one of the most critical parts of a device because it affects the user's experience. As I mentioned at the beginning, a bad user interface completely destroys a product. This particular camera has quite a good user interface. It has lots and lots of functionality, but it's been organized quite well. Of course, we have a high-resolution display for looking at pictures. That requires careful management. An electronic viewfinder is a second display. So when you look through the viewfinder, you're not looking through the lens. That's a bit pointless. It's done in DSLRs, but they're 1980s technology, really. I have no idea why they exist. So an electronic viewfinder does the job much better, but requires software support and electronic support. There are, of course, many controls. You may have a touch screen as well. This camera doesn't have a touch screen, but many new cameras do have exactly that, and that requires software management. So everywhere we look at the functionality of this camera, we see embedded software involved. The very last thing is storage. Of course, we use flash storage for storing our pictures. Happen to use SD cards as other possibilities. We need a lot of capacity, particularly if we're shooting in RAW or shooting in video. I find it quite interesting, because I do quite a lot of photography. I hear about people running out of memory in their cameras, and I have no understanding of what that means. I have a cheap memory card in my camera. I can take 2,568, I believe it predicts, raw images on that card. I run out of battery long before that, and run out of patience much sooner than that. So running out of memory is not a possibility nowadays. But I wanted to just to remind you of how far we've come with technology, and I'll have another reminder of that at the end of my talk. Because if I look at when I first had a digital camera back in 2003, I had a 500 megabyte, a half a gigabyte card, which I purchased in America for $300 US for a memory card. $300 for a memory card. That's what they cost in those days. I didn't like this, but that's what they cost. I recently bought a 128 gigabyte card for $40. We've moved on a bit, haven't we? And is it software's fault that we need these bigger and bigger cards, or is it just life? I'm not quite sure about that. But you know, in reality, the capacity is used, and I certainly couldn't manage with a half a gigabyte card now. But once again, the software area is storing the files. So a few conclusions and a couple of little stories. Well, the obvious conclusion is, in designing an embedded system, obviously hardware and IP are very important, but software is absolutely critical. The two go hand in hand, they can't be separated ultimately. One of the things that, as designers, we always have to look at is the end user and satisfying their expectations. Now, the users of devices now are increasingly what I call 21st century citizens. Nobody in this room is what I would call a 21st century citizen, I don't think, because these are people who were born in the 21st century. So all of us are 20th century citizens. It doesn't make us second rate, but it does change our attitudes. So I will give you an example. A friend of mine his name is Archie. He's actually the son of a friend of mine. As you can see, he's a nice little boy. This was taken a couple of years ago, this picture. And he takes a nice photograph, doesn't he? So, but when you take Archie's photograph, he wants to see it. He's very keen to look at the camera and see his picture on the back of the camera when you've taken it. If I said to Archie, oh, well, it's okay, I've taken your picture now, I'll get the film developed and we'll see the pictures next week, he would be unimpressed. And an unimpressed 3-year-old is not somebody you want to spend time with, I assure you. So, when you're designing systems, think about your end users, think about Archie, because he's the kind of person you need to consider his expectations. So I'd like to thank you for your time this morning, and I'll be around for a little bit longer. I have one more little story to tell you, just to wrap up, because I've noticed something out here in the world. Suddenly it's December, and so I have one greeting for you, of course, which is, I wish you Merry Christmas. Sorry, I don't actually like starting Christmas until about December the 23rd or thereabouts, if I can avoid it. But it gives me an opportunity just to tell you one more little story, which some of you will have heard before in a slightly different form, which is how far have we come? And I have a little prop here. I'll put my microphone down so I can just show it to you silently. A Christmas card. Would you love to receive a Christmas card like that? No, neither would I. It's actually, fortunately, it's really hard to buy electronic Christmas cards. Electronic birthday cards are readily available, but I made the wonderful discovery that it's hard to buy electronic Christmas cards. Why am I showing you this? It's partly to wish you Merry Christmas, but also just to add this last little nugget of information. The chip which is inside that Christmas card has more computing power than the lunar lander did in 1969. So think about that when somebody sends you one of these cards. They could have landed on the moon using that computer, but instead of that, they send you a Christmas card. So with that,